So we've been talking a lot about transforming a matrix into row echelon form or reduced row echelon form. So let's make some observations. First, observe that the row echelon form of a matrix is not unique. What do I mean by that? I mean that one matrix could be transformed into different possible matrices that are in row echelon form. Okay, so for example, 1 0 1 1 0 1 is in row echelon form, right? But I could transform it by taking 2 times row 1, moving that into my new row 1, into a different matrix. That matrix is also in row echelon form. Okay, and generally this is true. There's for any matrix, if we transform it into row echelon form, that's only one possible row echelon form representation of the matrix. There are going to be different row equivalent matrices to any matrix that are in row echelon form. But we do have the following theorem. The reduced row echelon form of a matrix is unique. That's one of the reasons that we like the reduced row echelon form. If you are able to transform a matrix using elementary row operations to its reduced row echelon form, that's the only reduced row echelon form for the matrix. There is no other possible reduced row echelon form. It is unique. Even if you use different row operations, go a completely different route, you will get to the same result. It's like all roads lead to Rome. Okay, you could start with one matrix, and then you get to the reduced row echelon form of the matrix, and doesn't matter which way you go, what row operations you take, you will always get to the same reduced row echelon form of the matrix. It is unique. Okay? But row echelon form is still useful. Even though it's not unique, there are some properties that are universal to all row echelon form matrices. Okay? In particular, the rank of a matrix is going to be unique. So let's define what that is. The rank of a matrix A denoted as the rank of A is the number of non-zero rows that remain after we reduce A to row echelon form. Using elementary row operations. Okay. Notice I didn't say which row echelon form. We know that generally a matrix will have multiple ways to express it in row echelon form. But all row echelon forms of a given matrix will have the same number of non-zero rows. Okay? We call it the rank of the matrix. It's also the number of leading entries because each row, each non-zero row of a row echelon form matrix has a leading entry. Okay? So that's the rank of a matrix. And we could use this to formalize some ideas we've already been thinking about. Suppose a system of m equations with n variables is consistent. Consistent here is the opposite of inconsistent. It means the solution has a solution. It means the system has a solution, at least one solution. Could be more solutions. Okay, but we're assuming for this theorem that this system of equations has a solution. It is consistent. Okay. Suppose the rank of the system, the rank of the coefficient matrix, of the system is R. Okay, so let's just paint the picture a little bit. We have m equations, we have n variables. Okay, so if we look at the coefficient matrix, then remember each row corresponds to an equation in the system. So we're going to have m rows. Remember that each column in the coefficient matrix corresponds to a variable in the system. Since we have n variables, we're going to have n columns. So this coefficient matrix is an m by n matrix, m rows, n columns. So an m by n matrix, meaning it has m rows and n columns. Okay? So we can make some observations here. All right? First, what happens if the rank of the matrix is equal to the number of columns or the number of variables of the system? Okay, then what? All right, so let's think about this. So let's imagine we get this into reduced row echelon form. Okay, so if R equals n, then there have to be as many non-zero rows as there are columns, right? The rank is the number of non-zero rows in the matrix when in row echelon form. So the number of non-zero rows is equal to the number of columns. And every non-zero row has a leading entry. So that must mean every column has a leading entry. And in reduced row echelon form, that must mean they all have a leading one. So we must have a 1 there, and a 1 there, and a 1 there, however many we have. Right? Let's say it's 3 for this example. Okay, so each column, if we have 3 columns, we must have 3 rows that are non-zero. We could have other rows that are 0, right? But we must have at least 3 non-zero rows because the rank is equal to the number of columns, the number of variables. And because we're in row echelon form, we have that stair-step pattern. It means that every column must have a leading entry in it. And so what that means is I could have whatever I want over here, as long as it's consistent. If I have rows of zeros here, I better have a 0 over here to make sure it's consistent, right? I am going to have a unique solution because this variable, this must be z equals 2. This must be y equals 7. This must be x equals 8. Okay? Now, this example is just one example, but it gives you the general idea. If the rank of the matrix is equal to the number of columns in the coefficient matrix, then the system has a unique solution. Okay? B, the number of free variables the system has is n minus r. Okay? Let's think about why that's true. And again, I'll just use an example to get the idea across, not a careful formal proof. But let's say that r is smaller than n. Okay, so let's just focus on the coefficient matrix for now. So again, let's suppose n is 4 actually. Okay, so say I have a non-zero row here, and maybe a non-zero row here. Okay. We have 1, 2, 3, 4 columns. Well, we've already seen that if we have columns without a leading entry in them, then they will be free variables. Okay? If I only have r non-zero rows, then that means I only have r non-zero leading entries. My rank tells me how many leading entries I have. If I have fewer leading entries than the number of columns, then I will have columns without a leading entry in them. So these columns do have a leading entry, but if I've got fewer leading entries than I have columns, I must have some columns without leading entries. And those columns are going to be my free variables. So the number of columns I have minus the number of leading entries is going to be the number of free variables the system has. Okay? In which case, if this number isn't 0, I will have infinitely many solutions. If r is less than n, the system has infinitely many solutions. So this is formalizing some of the ideas we've already developed. So we'll take a more careful look at this to make sure we get some more intuition on what's going on here. Do notice that either r is going to be equal to at the end, the rank is equal to the number of columns or the rank is less than the number of columns. I cannot have the rank be greater than the number of columns. That's not possible because the rank is the number of non-zero rows when in row echelon form. And each row has a leading entry. Each leading entry must be in its own column. So if I have a leading entry here and a leading entry here and a leading entry here, and that's all the columns I have, I can't have another leading entry in the next row because I don't have any more columns to put it in. Each leading entry has to be in its own column so we can get that stair-step pattern. Otherwise, we wouldn't be in row echelon form. Okay, so these really are the only two possibilities. Either the rank of the matrix is equal to the number of columns or it's smaller than the number of columns. If we have a consistent system and the rank is equal to the number of columns, then we have a unique solution. If we have a consistent system and the rank is less than the number of columns, then we have infinitely many solutions. And I do want to emphasize one more time, we are assuming here that the system is consistent. If the system is inconsistent, then of course we have no solution, and we do not have to consider this theorem. Remember, we have an inconsistent system if when we put the augmented matrix in reduced row echelon form, we get a row of all zeros with something not a zero at the end, like a 1. Okay, that would mean that we have an inconsistent system. And so our system in that case would have no solution.